Salam, peace be upon you. My name is Muhammad Layat Siddiqui, the father of Holophase. Part 26. Phase versus group. Meaning. Remember the language we are learning together? There is one field, phi, the holophase. One continuous cyclic movement from which all of reality unfolds. When phi begins to change, its first derivatives appear, and with them, three dimensions show themselves at once. Time as omega, space as k, and motion as v, build from both. Every higher derivative is a finer question about how phi changes, and each one casts three shadows together: a time shadow, a space shadow, and a motion shadow. These echoes mix and weave into one another, forming the patterns we call fields, particles, bodies, thoughts, and worlds. In this picture, everything that exists is a living tapestry of phi, endlessly echoing through its derivatives and their dimensional shadows. Today, we listen to just one of those echoes. In our last journey, we learned the universe's grammar. We discovered dispersion rules, the fundamental syntax that links temporal rhythm, omega, to spatial texture, k, and defines which waves can travel in a given medium. This grammar is the first rule of wave semantics, the foundation of how patterns propagate. But once a wave exists and travels, a new and profound question arises. What exactly is moving? Is it the crests and troughs themselves, the visible pattern of the wave? Or is it something deeper, the pulse, the signal, the meaning carried by that wave? Today, we discover that within a single wave phenomenon, there are actually two distinct kinds of motion, two different verbs of travel. We explore part 26, phase versus group meaning. This is where we learn that the universe speaks in layers. It has a surface dance and a deeper current underneath. Understanding this distinction is not just a technical detail. It is essential for reading how information, cause, and influence actually flow through the world. Our Ep.7 climb has brought us deep into Chapter 6, Wave Semantics. Having grasped the grammatical rules, dispersion, we now examine the two primary verbs that this grammar produces. This is a natural and crucial step. First, learn the rules of sentence formation. Then, learn the different kinds of actions those rules allow. This distinction will be key to everything that follows in wave semantics: information transport, wave packets, and wave interaction. Imagine you are at sea, watching a steady train of ocean swells approach the shore. You fix your gaze on one particular crest, one clear peak in the water. You track that peak as it moves toward the beach. The speed at which that specific crest travels is called the phase velocity. It is the speed of the waveform itself, the speed of the repeating pattern of highs and lows. It is like picking one dancer in a chorus line and watching how fast that individual dancer moves across the stage. Now shift your attention. Instead of following a single crest, look at the group of waves as a whole. Notice where the waves are tallest and most concentrated, where the energy is gathered. This region of high activity is the wave group or the wave packet. You will see that this lump of energy, this packet, moves at a different speed. Often, it moves more slowly than the individual crests. The crests seem to appear at the back of the group, march through the middle, and disappear at the front. The speed of this envelope, this moving lump of activity, is the group velocity. Here is the heart of the distinction. Phase velocity answers the question, how fast does the pattern repeat itself in space? In formulas, people sometimes write this as v phase equals omega divided by k. It is the speed of a point of constant phase, the speed of one crest, one trough, or one zero crossing. Group velocity answers a different question. How fast does the modulation, the packet, the information travel? In formulas, people write this as v group equals d omega divided by dk, the slope of the dispersion curve. It is the speed of the envelope, the speed at which energy or a signal propagates. In a non-dispersive medium, like simple sound in air or light in a vacuum, where the dispersion relation is a straight line, omega proportional to k, these two speeds are equal. The dancer and the message move together as one. But in a dispersive medium, like light in glass, surface waves on water, or quantum matter waves, the dispersion relation is curved, not a straight line. In these media, phase velocity and group velocity diverge. They become two different numbers, telling two different stories about the same wave. This is where the semantic richness begins. In the holophase language, phase and group velocities represent two distinct semantic verbs of motion. Think of someone speaking a sentence. The storm approaches. The phase velocity is like the speed of the vibrations of the speaker's vocal cords, the rapid cyclic motion that creates the sound waves themselves, the pitch, the tone, the ringing structure of the sound. This is the how of the sound's physical production. The group velocity is like the speed at which the meaning of the phrase, the storm approaches, crosses the room and reaches your mind. It is the speed of the information, the message encoded in that sound. Both are essential. Without the phase vibration, there is no carrier wave at all. Without the group propagation, the message does not arrive. But there are different actions. One is the carrier's rhythm, the other is the message's journey. In the master tree, this distinction arises directly from the structure of the dispersion rule. The phase velocity, omega over k, is a simple ratio built directly from the first derivatives of phi. How quickly phi is changing in time compared to how quickly it is changing in space. The group velocity, d omega over dk, is a mixed derivative. It tells us how the temporal rhythm changes when we vary the spatial texture. It is our first encounter with the derivative of the dispersion relation itself. That already places group velocity at a higher node in the wave semantics branch, where we begin to see the consequences of grammatical nuance, not just the bare grammar. Operationally, the two velocities emerge from how we construct real signals in the world. A perfect infinite sine wave with a single pure omega and a single pure k is a mathematical idealization. It has a well-defined phase velocity, but it carries no real information. It is more like a constant dial tone, the same pattern forever. To send a message, a click, a short pulse, a word, a bit of data, we must modulate the wave. We create a packet by superposing many different omegas and k's that are close to each other in value. This superposition produces a localized pulse, a lump that appears, travels, and then fades. This packet has an average omega and an average k. The crests inside the packet move with the phase velocity corresponding to that average pair. But the packet as a whole moves with the group velocity, which depends on how omega changes with k around that average, the slope of the dispersion curve nearby. A helpful analogy is a marching band. Phase velocity is like the speed at which each individual marcher is stepping and moving. Group velocity is the speed at which the band's formation, a square, a line, a rotating shape, moves down the street. The individual marching speed can be different from the speed of the overall formation. In a dispersive medium, the way the different frequency components line up, which is captured by the slope d omega over dk, is not trivial. So the formation, the packet, moves at its own pace, distinct from the pace of the individual oscillators, the crests. Both velocities have full dimensional meanings, but they highlight different aspects of the dimensional echo. From the time perspective, phase velocity tells us how quickly a specific phase of the oscillation, like a peak or a trough, passes a given point in time. It is about the travel of local timing. Group velocity tells us how quickly a temporal landmark, like the arrival of a pulse or the peak of an envelope, reaches a distant point. It is about the travel of events that carry information. From the space perspective, phase velocity describes the motion of the fine-scale pattern, the ripples, the stripes, the detailed texture. Group velocity describes the motion of the coarse-scale envelope, the outline that contains those ripples. From the motion perspective, we learn something deeper. Propagation itself has two layers. In a dispersive system, if someone asks, "How fast is that wave moving?" the honest answer is, "It depends what you mean." The crests move at the phase speed, but the signal moves at the group speed. The thing that is moving is composite, and its components have different kinematic identities. In our map of wave semantics, Phase and group velocity represent the first major fork in the branch that grows out of the dispersion node. The branch starts at the dispersion rule and immediately splits into two directions. One path leads to phase velocity, a simpler concept given by a ratio, built directly from the core alphabet of omega and k. The other path leads to group velocity, a more subtle concept that depends on how omega responds when k is varied. This group velocity path feeds into envelope evolution, information transport, and many higher dynamical effects. This fork is semantically critical. It tells us that the naive idea of wave speed is too coarse, and that resolving this ambiguity is necessary if we want to understand how the universe transmits anything more interesting than an endless hum. These two velocities also interact differently with other branches of the language. With the mixed hour, group velocity is a prime example of a mixed derivative, d omega over dk. The curvature of the dispersion relation, the second derivative, d squared omega over dk squared, gives the group velocity dispersion, which controls how wave packets spread, sharpen, or distort as they travel. This directly links phase versus group meaning to envelope evolution, which we discussed earlier. With information transport, the link is even more direct. Information, in any physical medium, travels at the group velocity. This is the speed at which cause and effect, in the form of signals, can move. In some unusual media, the phase velocity can exceed the speed of light. But this does not violate relativity because no new information or causal influence travels at that speed. Only the pattern of crests appears to move quickly. The news itself, the modulation, is still limited by the group velocity, which respects the deeper constraints of the medium and ultimately of space-time. In certain exotic materials like photonic crystals or topological insulators, the dispersion bands can have special shapes. Group velocity can become very small, so that packets are effectively stopped, or even negative, so that the envelope appears to move backward while the internal phase pattern moves forward. These behaviors are deeply tied to the topological structure of the dispersion relation in momentum space. Quadratic balances in the underlying equations further connect phase and group velocity. For example, in simple relativistic settings, the product of phase velocity and group velocity for light in vacuum equals the speed of light squared. These relationships are signatures of deeper symmetries and conservation laws in phase dynamics. The semantic meaning of this distinction can be captured in a simple phrase. Phase velocity is the verb of appearance. Group velocity is the verb of influence. Phase velocity tells us how the stage scenery moves, how the detailed pattern of crests and troughs glides across the background. Group velocity tells us how the plot advances, how the story, the change, the influence travels from one place to another. This allows the holophase language to separate the medium's inherent rhythm from the message carried on that rhythm. It explains how you can have very fast phase motions, even apparently superluminal pattern speeds, without breaking the fundamental limits on causality. It is the language's way of separating style from substance in the realm of motion. For a given medium and a given part of its dispersion curve, phase and group velocity are stable properties. They are part of that medium's identity. At the same time, the relationship between them can vary dramatically across different frequencies. In what is called normal dispersion, the group velocity is smaller than the phase velocity. In anomalous dispersion, the group velocity can be larger than the phase velocity. At special points in the dispersion curve, the group velocity can become zero, so that the envelope is effectively stationary while phase ripples still slide through it. Cleverly engineered materials can even produce a negative group velocity, where the envelope appears to move backward. None of these effects contradict causality. They simply reflect complex ways in which modulation and carrier can interact within the rules of the medium. All of this is testable. The key prediction is that in a dispersive medium, a modulated signal, a pulse, will arrive at a time determined by the group velocity, while the internal oscillation pattern inside that pulse will move according to the phase velocity. In the lab, one can first create a nearly pure monochromatic wave and measure its frequency and wavelength, giving a phase velocity. Then, by modulating that wave to create a packet, and sending it through a piece of dispersive material, one measures when the packet's peak arrives at a detector some distance away. That arrival time reveals the group velocity. Careful experiments in optics, acoustics, water waves, and many other systems consistently confirm that it is the group velocity that dictates the overall signal's arrival, not the phase velocity. This split between phase and group motion shows up in many natural phenomena. In optics, when white light enters a prism, different frequencies travel with different phase velocities in the glass, causing them to bend at different angles and separate into colors. The rainbow of outgoing light is governed by the dispersion relation, and the way a pulse stretches in time as it travels through the glass is controlled by the group velocity and its dispersion. In the ionosphere, high-frequency radio waves can have a phase velocity larger than the speed of light in that medium, but the modulated radio programs, the voices and music, travel at the group velocity, which remains subluminal. In Cherenkov radiation, a charged particle moves through a material faster than the phase velocity of light in that material, generating a shock wave of light, the familiar blue glow in nuclear reactors. Here, the condition is that the particle outruns the phase wave, not the ultimate speed of information in vacuum. On the ocean, long swell generated by distant storms offers a beautiful example. The long wavelength waves have a higher phase velocity, so their crests outrun the shorter, choppy waves. At the same time, the actual energy transport, the growth and decay of the sea state, is governed by the group velocity, which for deep water waves is about half the phase velocity. So from a far-off storm, you may first see long, gentle waves arrive, then later feel the full strength of the storm's energy as the bulk of the packet arrives at the group speed. In quantum mechanics, an electron in a crystal is described by a wave packet built from allowed wave vectors in the crystal's band structure. The oscillatory phase of this wave is associated with a phase velocity, while the motion of the electron's probability density and charge, the thing we measure as current, travels at the group velocity, derived from the slope of the band structure. This pattern of a fast carrier rhythm and a slower, structured content appears in human systems as well. The constant churn of the 24-hour news cycle, the endless updates, ticker tapes, and commentary is like the phase velocity, the basic rhythm of the medium. A specific story, for example a scandal or a breakthrough, is like a wave packet. Its spread through society follows its own group velocity, governed by attention, networks, and relevance, not by the raw speed of the cycle. Social media feeds scroll at a high phase velocity. New posts appear all the time. But a truly viral piece of content, a meme or a video, moves through the network as a group. Its spread rate depends on sharing patterns and algorithms, the dispersion rules of the platform, not on the user's scrolling speed. In economics, the rapid flicker of prices during intraday trading is like phase motion. Larger economic shocks, such as a financial crisis or a major policy change, are like packets. They propagate over days, weeks, or months at a slower group speed, determined by institutional structures and feedback loops. In history and culture, daily routines and seasonal rhythms are the carrier. Major movements and shifts in worldview are the packets that move through those rhythms at their own pace. In the brain, background neural oscillations provide rhythmic carriers, while patterns of coordinated activity, representing thoughts, perceptions, or decisions, behave as packets that travel across networks at an effective group velocity distinct from the carrier frequency. You can train yourself to see and feel this distinction. Watch ripples on a pond after you drop a pebble. You will see the individual crests moving outward, and you will also sense the broader circular region of disturbance, the packet, expanding at its own rate. On a highway, notice how the boundary of a traffic jam, where moving cars meet stationary ones, often moves backward relative to the cars. That backward moving boundary is like the group velocity of a congestion wave. Inside the jam, individual cars lurch forward and stop. Those local motions resemble the faster phase activity inside a slower envelope. Even in your own body, when you feel your pulse at your wrist, there is an underlying waveform, the pressure oscillation as the heart contracts and relaxes, and there is the arrival of the pulse as an event, carrying information about when the heart beat. We now return to phi with this deeper appreciation. Phase and group velocities are not separate, alien entities. They are two different readings of the same underlying propagation of phi. Phase velocity reads the fine print, the local cycling of the field. Group velocity reads the headlines, the movement of coherent changes, the tally of modulated activity. Both emerge naturally once phi behaves as a cyclic field that can be modulated, and once the dispersion grammar is non-trivial. The distinction is a necessary consequence of phi supporting not only pure tones but also packets, not only bare oscillations but also meaningful signals. With this understanding, our wave semantics branch becomes more complete. We now hold the key to deciphering how signals move, how causes lead to effects, and how information navigates the grammatical landscape of the universe. In the next part, we will ask a more direct question. What exactly is this news that rides on the group velocity? What is being transported in these traveling groups? We will move into part 27, Information Transport, where we explore how the holophase language encodes meaning, data, and influence in the modulated patterns of phi, and how group velocity is the absolute speed limit for any such story inside a given medium. But for now, listen and watch for the two speeds. In the shimmer of light, in the roll of sound, in the flow of ideas, and in the pulse of life, notice the dancer and the message, moving in their distinct but intertwined ways. You are perceiving the dual verbs of motion in the one unfolding sentence of phi. Peace be upon you. Until part 27.